Hi, we are looking into conjugate gradient algorithm, which is a class of Krylov subspace methods for symmetric A matrix. When you are solving x is equal to b using Krylov subspace based iterative methods, if the matrix A is symmetric, we have observed that few interesting properties come out. One is that the new residual vector is along the present residual vector is along the next steps next basis of Krylov subspace at particular m level, or residual vectors are orthogonal to each other. And also we have seen that the auxiliary vector P m has an Pi has an A conjugacy, that is Pi dot A P j is equal to 0 if Pi is not is equal to P j. Utilizing these facts, we have found out how alpha x and x r and p should be updated and what should be the values of the updates. So, if we summarize what we have found out, the crux of that alpha and beta at any iteration stage, or for any particular, when we are going in Krylov subspace, any particular basis of the Krylov subspace, we can write alpha and beta is r j dot alpha is r j dot r j divided by a p j dot r j, and beta is r j plus 1 dot r j plus 1 divided by r j dot r j, and r j is the residual and p is the auxiliary vector, and x can be updated as x j plus 1 is x j plus alpha j p j, r j plus 1 r will be a residual will be updated as r j minus alpha j a p j, p j plus 1 is equal to r j plus 1 beta j p j. So, if we translate this into an algorithm, all are basically vector operations, vector products, etc., except we have to find out this A P matrix vector product, which are used at couple of stages here. So, what we should do? We should start with a guess x 0, which will give us the initial guess r 0, which initial residual r 0 x 0 minus b, and set the initial auxiliary vector is same as the initial residual vector p 0 is equal to r 0, and then we will update everything, obtain alpha and update x and r, which are updated based on alpha, and then update beta. Once r is updated, we get r j plus 1, we can calculate beta, obtain b using the updated r. This is the updated r, this is the updated r, use the updated r to obtain b, and update p based on that. So, start with 0, m is equal to 0, you obtain alpha 1 obtain, and this is x 0, you have p 0 and r 0 everything there. So, with alpha 1 you find out x 1 is equal to x 0 plus alpha with alpha 0 rather plus alpha 0 p 0, and r 1 is equal to r 0 minus alpha 0 a p 0. Once you found r 1 dot r 1 divided by r 0 dot r 0, you find out beta. P 1 is equal to r 1 plus beta 0 p 0, update p, and then go to j is equal to 2, 3, 4 up to m, update p, and iterate for convergence. Convergence means what should be the convergence criteria? That is what we have, the idea we got from the basic iterative methods, that mod of x j plus 1 minus x j is less than some small number epsilon, say epsilon 1, or the residual r j plus 1 must tend to 0, r is equal to b minus x. Once we have solved the equation, r must go to 0, or we can also check whether r j plus 1 is less than a small number epsilon, another small number epsilon 2. We can fit a convergence criteria based on the difference of last two guess values, or based on the absolute value of the or norm of the residual vector r. If the residual vector is very small, it should go to we will say that it has been converged and converge in that way. So, we are basically what we are doing, we are basically finding out different basis of the Krylov subspace A R0, A R0, A square R0 this, and along each basis we are updating x. So, P is, because we are updating along x along P becomes essentially the basis of Krylov subspace. P's are orthonormal to each other also. So, P becomes basically the normal basis of Krylov subspace, so you can orthonormalize it easily. So, instead of finding out the orthonormal basis V1, V2, Vn, we are looking into the auxiliary vector P1, P2, Pn, and they become the basis now. And we can say that P0 is equal to R0. So, R0 is one of the vectors which will span the Krylov subspace. And how R1, R2, Rn, we see that we will finally with this P we are spanning the Krylov subspace. So, increasing number of M, we are approaching the right solution, so that the residual Rm goes to 0. So, now if we look into the algorithm in a more formal form, compute R0 is B minus AX0 and P0 is equal to R0 for j is equal to 0, 1 until convergence. That means residual is, so let us write down convergence can probably be checked here, that mod Rj plus 1 is less than epsilon, check it. Obtain alpha j is Rj dot Rj by Apj dot Pj, xj plus 1 is equal to xj plus alpha j Pj, Rj plus 1 is Rj minus alpha j Apj, and once you obtained Rj plus 1, you already have stored Rj dot Rj. This Apj, once you find this and utilize it here, so that you can avoid doing the matrix multiplication several times. You have stored Rj dot Rj and then Rj plus 1 divided by this Rj dot Rj which you have stored, you get beta j, and Pj plus 1 is Rj plus beta j Pj, and then you, if mod Rj, so here you check if mod Rj is less than epsilon, if then do you come out of the iteration loop, say that the solution has converged, else you keep on iterating it for the right solution. This is the algorithm, though the mathematical formulation deals with number of steps and manipulations using matrix algebra, the algorithm looks very simple. It is also extremely straightforward to write a computer program for this, which will give us good result. But this is always for, this has to be remembered, this is for symmetric positive definite. If A is not symmetric, this algorithm will fail. Now, let us look into the performance, and which is interesting. So, there are few n into n matrix. So, we have a n into n x n is equal to b n. We have a n into n matrix, and we started the changing the values of n from 16 to 256. So, finally, we are solving 256 into 256 equations, and the convergence criteria is kept very small, 10 to the power minus 11, etc. So, what we can see is that Jacobi takes 1253 iterations for this particular matrix. Gauss-Seidel takes half of that. SOR with optimum over relaxation factor takes further smaller value. However, minimum residual and steepest descent takes 1300 iterations. Conjugate gradient takes only 32 iterations, and we can check this is twice n basically number of iterations. For n is equal to 32, Jacobi, Gauss-Seidel, MR etc. takes around, Jacobi, MR, SD, they are comparable, takes around 4,800 iterations. Gauss-Seidel takes to 2200, SOR with optimum over relaxation takes 760, and conjugate gradient takes 63, which is almost twice of n. And these things continue, that the number of iterations in conjugate gradient is much smaller than the number of iteration in any other of them. So, it is for symmetric positive definite matrix S, conjugate gradient is the very first solver. When Jacobi is doing 16,000 iteration or 2,15,057 iterations, for a better convergence conjugate gradient is only doing 484 iterations. Another interesting thing we can see that if we compare between steepest descent or MR with conjugate gradient, steepest descent with conjugate gradient, steepest descent with conjugate gradient, the number of iterations are almost square root of that. So, the convergence rate is almost square for conjugate gradient compared to the steepest descent algorithm, or even is very high compared to any other algorithm. So, for symmetric A matrix, this is one of the fastest solver till we know, and the number of iterations are of the order of number of rows in the matrix. If we keep the convergence criteria smaller, all these numbers will also fall down. However, this is very important aspect. Also, there is one matrix vector product and few vector products. So, if we compare the number of floating point count per iteration, rather floating point count per, we can see that this is of n square plus n, which is actually less than successive relaxation or steepest descent. So, conjugate gradient is a very fast solver, as well as the number of iterations, number of floating point operations per iteration is small. So, number of iteration is small, number of operations per iteration is small. So, in as a whole it will give us a very fast solver, an extremely fast solver, and the number of iterations are usually of the order of n. Why is it fast? For that we will quickly look into the convergence criteria of conjugate gradient method. Let xm be the approximate solution obtained at the mth step of conjugate gradient algorithm, and x star be the approximate solution, and we define eta is lambda mean by lambda max minus lambda mean. Then x star minus xm, it is a norm. So, what is a norm? Y is a norm is equal to y transpose a y. So, x star minus xm's a norm is equal to x star minus x 0, x star is the exact solution, xm is the mth iteration solution, a norm by polynomial of 1 plus 2 eta, and this polynomial Cm, so Cm is a function of 1 plus 2 eta, it is not Cm into 1 plus 2 eta, Cm is a function of 1 plus 2 eta. This polynomial Cm is known as the Chebyshev polynomial of degree m of first kind, not going into detail, but it is the polynomial of 1 plus 2m. If you can simplify this, that k being the spectral condition number lambda max of matrix A, lambda max by lambda mean, xm by x star minus xm is of a norm is less than equal to twice root of spectral condition number minus 1 by root of spectral condition number plus 1 to the power m x star minus x 0 by a. So, convergence is a function of convergence remains a function of root of spectral condition number, and as small is this number, it will converge first. Now, earlier for steepest descent we have seen that convergence is a function of spectral condition number. Spectral condition number is a number greater than 1, is the relation between lambda is lambda max by lambda mean. So, it is always greater than 1. Root of spectral condition number must be smaller than the spectral condition number. So, this particular coefficient which is being multiplied with x star minus x 0 to see the mth order error must be a smaller number than the coefficient which was multiplied with the same norm for steepest descent algorithm. And how smaller? This is root of spectral condition number or a spectral condition number in square root. So, in a way we can get the idea that the rate of convergence or the convergence factor will be rather rate of convergence convergence factor will be in a sense square root of that. Therefore, the number of iterations will be also square root of the number of iterations for steepest descent method. And that is why conjugate gradient is a very fast solver, because its convergence depends on the root of the spectral condition number, and the number of iterations are almost square or of the order of square root of number of iterations needed for steepest descent type of algorithm. So, we get an algorithm which is robust, which can handle any A which is symmetric positive definite and is a very fast solver. What is the advantage in conjugate gradient method, considering the fact that it is a Krylov subspace method? Because Krylov subspace methods need inversion of a of the Heisenberg matrix HM of a upper triangular matrix with one subdiagonal, need inversion of that matrix, and De-Langstroth algorithm needs a TDMA type of method to solve this particular equation where HM is replaced by a tridiagonal matrix TM. Inverting even or even applying like a TM inverse or HM inverse, doing these things even if TM is a tridiagonal matrix, they are expensive than this particular method, because it does not use recursive method, it does not use matrix inversion, it uses a method through which the auxiliary vectors are advanced utilizing the factor that they are A conjugate, and the residual vectors are obtained at next level, assuming that one residual vector is orthogonal to all the previous residual vectors. So, using these properties we can formulate linear relationships for advancing residual vector as well as the auxiliary vector, and then we can very easily advance the xm plus 1 to the or the solution x to the next iteration level, and it converges very fast due to the as the function is convergence is a function of root of spectral condition number. So, considering all this, conjugate gradient becomes a very fast solver, and though it is a solver of the Krylov subspace methods which belongs to Krylov subspace method, however, it does not explicitly find out HM inverse or solve TMY is equal to beta E1, rather it uses some properties like A conjugacy of auxiliary vector and RMs orthogonal to each other, and devises a faster way to solve the Krylov subspace problem. Now, this is a very good method, however, this is restricted only for symmetric matrices. And now, our question will be what will happen for a general sparse matrix which is not symmetric. So, what are the first methods based on Krylov space for that? And for that we will start looking into oblique projection methods. We will start a discussion very soon on oblique projection methods, and after that we will look into different type of Krylov subspace methods. Once we finish some discussion on oblique projection method, different types of Krylov subspace methods. So, let us quickly look into the generalized method for any matrix. We will not restrict ourselves to positive to symmetric positive definite matrix for any matrix, which is called a GMRES method or generalized minimum residual method, and it is an oblique projection method. So, Krylov subspace matrix solvers, this is a projection method that seeks an approximate solution xm from an affine subspace x0 plus km by imposing condition that B minus xm or the residual is orthogonal to Lm. Lm is another subspace of dimension m, x0 is initial guess. In case of Krylov subspace methods, this space Km is Km of A and R0, R0 is the initial residual, where Km is spanned by R0, A R0, A square R0 to the power m minus 1 R0. And till now we have looked into orthogonal methods where Lm is equal to Km, which are called the orthogonal methods. And now we will look into GMRES, which is an oblique method, oblique projection method, as Lm is not is equal to Km. B minus Axm is not orthogonal to Km, rather it is orthogonal to Akm. So, let us see what do we mean by that. The idea of generalized projection method, generalized minimum residual method is, this method is a projection method based on taking Lm is equal to Akm, in which Km is the mth Krylov subspace, starting with the first basis of Krylov, that Krylov subspace B1 is R0 by mod of R0, first orthogonal unit base, orthonormal basis of that. And through this technique, so starting with V1 is equal to R0 by mod R0, we will find out one basis for Km, and rather will later we will find out other orthonormal basis for Km and find out the Km, and then we will get Lm is equal to Akm and propose a general projection method, and this method is called generalized minimum residual method or GMRES. This technique minimizes residual norm of B minus x over all vectors x0 plus Km. So, instead of minimizing x transpose Ax minus x transpose B, what we are doing for conjugate gradient method, now we are minimizing B minus x. And if we try to relate this with general projection methods, we will see that this minimization happened in minimum residual or MR method. Now, MR was a 1D projection method. When we try to generalize MR, we get the generalized minimum residual, the generalized minimum residual method GMRES. From 1D to multidimensional general projection method, if we go, we get GMRES. The implementation of this algorithm is based on an approach which finds the basis of Km first, which is similar to FOM, full orthogonal method. In full orthogonal method, Km is equal to Lm. In FOM, full orthogonal method, Km was same as Lm. Here we will find out Km exactly the way same we or rather I will write it opposite. In full orthogonal method, Lm is same as Km. Here we will find out Km which is similar to FOM. However, in GMRES we will find out Lm which is not Km, rather is equal to Akm. But how will we find out Km? That will be same as FOM. So, all the Heisenberg matrix, all the basis of the Krylov subspace, everything will be exactly same how we have found out our Krylov subspace and the Heisenberg matrix basis Vm and Hm in full orthogonal method, all will be exactly same. Now, once we have found out Km, we will do something else. And the best thing about this method is that this method works for any non-singular matrix. So, we are now not limited to symmetric matrix. For non-symmetric matrix, for non diagonally dominant matrix, for all these matrices. This method works for all these matrices. If you remember, MR minimum residual method was also effective for all these matrices. However, that was dependent on that is a typically slow method, because convergence rate is dependent on the spectral condition number of A transpose A, where the spectral condition number usually becomes much higher than the spectral condition number of A. So, it is a minimum residual method was a slower method, considering other methods of that particular class. However, this GMRES is will be faster than minimum residual method, but as minimum residual method it can work for any type of non-singular matrix. So, finding basis for Km is same as what we have done in Arnoldi's method, Arnoldi modified Gram-Schmidt method, which is the say which will be continued to full orthogonal method later, that you start with create a vector of norm 1 and then you find out W is equal to find out Hij, which are the parts of the Heisenberg matrix Hij, and you find out Vj, which are the basis vectors for the orthonormal basis of Krylov subspace, and you start with V1 is equal to mod R0 sorry V1 is equal to R0 by mod R0. You will follow full orthogonal method, where the Krylov subspace is span of R0, A R0, A square R0, so on a to the power m minus 1 R0. So, you start with the initial guess to be initial first vector, the V1 to be the initial residual normal in normalized form, and you get the basis vectors of the Krylov space you need for solving x is equal to b, and Hij are the members of the Heisenberg matrix H bar m. So, we will use H bar m and Hm, H bar m, we will use H bar m and Hm in some cases. From H bar m, if we remove the last row, it becomes the another Heisenberg matrix, which is Hm. Any vector x in x0 plus km can be written as x is equal to x0 plus vmy, where y is a m vector and vm are the orthonormal basis functions of Krylov space, and this is same as Arnoldi or FOM method. Now, if we define Jy as b minus x L2 norm, or if I substitute x is equal to b minus x 0 plus Vy is L2 norm. Now, b minus x is equal to p minus x 0 plus Vym, which is R0 minus a Vym. From Arnoldi's algorithm, we have seen that V1 is R0 by mod of R0 and mod of R0 is given as beta. So, we can write, and we have also seen from Arnoldi's algorithm Vm is Vm Hm Wm Em transpose, which is Vm plus 1 into Hm bar, the full Heisenberg matrix. So, if we substitute this here, we can write b minus Ax is R0 minus Avmy, and Avm, this Avm can be substituted as Vm plus 1 Hm bar, and R0 can be written as beta V1, which comes from here. R0 is equal to beta V1, which is E1 becomes the first unit vector 1 0 0. This is beta E1 minus Hm bar y Vm plus 1. Vm plus 1 is the basis of the orthonormal basis of Krylov subspace. So, we got an expression for B minus Ax. Since the column vectors of Vm plus 1 are orthonormal, we can write Jy is B minus Ax, second norm is B minus X0 plus Vmy second norm, and beta E1 minus Hm bar y Vm plus 1 second norm. The relation we exactly got beforehand, that beta B minus X is beta E1 Vm plus 1. So, since Vm plus 1 has orthonormal columns, this is beta E1 minus Hm bar y. Now, the GMRES approximation is finding out the unique vector x0 plus k, which will minimize Jy. That is, xm will be x0 plus Vmym, where ym is the value of y for which beta E1 minus Hm bar y is minimal. And this is the idea of the GMRES method, that you find out minima of Jy, which is beta E1 minus Hm bar y, and you start that Jy is equal to beta minus X2. Find out the minima of that, which is finding minima of beta E1 minus Hm bar y, and with this Ym, Vm you have already found out using Arnoldi or FOM type of method. With this Ym you find out xm is equal to x0 plus Vmym, which is the solution. This xm is the solution of Ax is equal to b, approximate solution of Ax is equal to b. Now, this is, instead of solving X is equal to b, what you have to do is you have to find out minima of beta E1 minus H bar My. However, the minimizer is inexpensive to compute, as it requires solution of m plus 1 into m least square problem, where the value of m is typically small. And with this idea, we will move further and we will see how we can propose an algorithm for GMRES and what are the convergence criteria for that. Thank you.